Hello everyone, I'm Daichi Fujiki from the University of Michigan. Today I'm gonna talk about our work on SeedEx, a genome sequencing accelerator for optimal alignments in subminimal space. Genomic is said to transform medicine. For example, typically a drug is prescribed population-based without considering specific responses originating from individuals' genetic content. But it will be nice if we can make an individualized treatment plans, and that's the promise of precision health. It's becoming promising today because the genome sequencing cost has decreased tremendously over the last decade by more than 1,000 times. What is more, you no longer have to use a huge instrument for sequencing because portable sequencers are becoming common. In order to get meaningful diagnosis and insights from your specimen, first you pass it through sequencers that produce small chunks of genome strings called reads, and then you have a sequence of time-consuming analysis steps, and finally you can get data for a diagnosis. This whole pipeline takes several days to weeks. In this work, we target one of the computationally intensive steps called read alignment. The goal of read alignment is to map the reads to reference genome, which is the standard human genome assembled by Human Genome Project. Read alignment has two phases, seeding and seed extension, and it takes around 300 CPU hours on BWMM, which is the community standard software solution. The first phase is called seeding, which provides candidate position on reference genome where the read could potentially match. Then, in seed extension, we compare the reference strings with the read, score the similarity, and pick the best position. The scores are provided by solving an approximate string matching problem of reference and query. The similarity between two strings are typically measured using weighted Levenshtein distance, which is based on the minimum number of insertion, deletion, and substitution required to match the strings. Typically, Smith-Waterman algorithm is used for seed extension, and it has been leveraged in both software and hardware. It first fills n-square matrix using dynamic programming. Then it traces back the path which gives the best score. Smith-Waterman algorithm scales quadratically with the string length n. There is also a banded version of Smith-Waterman which calculates scores within the band of size w and provides alignment with edits up to 1/2 of w with order of wn complexity. Hardware accelerators typically use a popular historic array with order of WPEs. While widely used BSW algorithm cannot always achieve optimal alignments, we argue that guaranteeing optimality is essential. First, the differences in human genomes are very small, which is about 0.1%. Because accurately capturing variance between genomes is the ultimate goal of genome sequencing, even small errors in alignment can lead to expensive clinical mistakes in critical disease diagnosis. Second, ensuring equivalency to the standard aligners is important because several research and clinical applications rely on well-known clinically validated behavior of alignment tools. So, even small seemingly innocuous differences in output could require costly revalidation of pipelines and becomes a barrier to practical usability. Recently introduced BWMM2 adheres to this policy and guarantees to produce a bit equivalent results as BWMM. In fact, there are many challenges in guaranteeing optimality in current hardware accelerators. A naive approach can use a wide full-band PE arrays, but guaranteeing optimality of the results generally requires a really large number of PEs. Moreover, this makes edge PEs severely low utilized because we identify that more than 98% of programs use only 10 PEs at the center of the band. If we use a narrow band PE arrays, it can miss the optimal path. The only way to guarantee optimality is to use the worst-case estimation of required band, which is calculated by software based on the string length. However, even with the state-of-the-art algorithm, we can only obtain really conservative estimation, as you can see in the figure. We plot band size versus software execution time and hardware resource utilization. Software can afford full band thanks to the kernel's RE termination optimization at the runtime. However, because we cannot resynthesize hardware at the runtime, band size appears as a fixed area cost. SeedEx breaks this dilemma and takes the best of these two, optimality guarantee from the full-band design and the area efficiency from the narrowband design. We adopt a speculation and test-based approach where we speculatively use narrowband PEs and check if optimality can be guaranteed. If not, we fall back to CPU or a full-band machine. This is the overview of SeedEx. We present SeedEx algorithm, which is a speculation and test-based algorithm to check the optimality of narrowband score, and SeedEx Accelerator, which is a very efficient embodiment of SeedEx algorithm in hardware using several hardware-specific optimizations, and we integrate SeedEx with BWMM and deployed it on AWS Cloud FPGA. Now let's start with SeedEx algorithm. SeedEx algorithm is composed of three checks. The first check, thresholding, calculates the theoretical upper bound scores outside a band and compares it with a narrowband score. If it fails, we perform E-score check, which eliminates the path entering the red region from the top by calculating optimistic score of such paths. Finally, a distance check performs supplemental score calculation using lightweight edit machines to eliminate a path entering from the left. The first check, thresholding, calculates the theoretical highest score of the regions outside the band and compares it with a narrowband score. The score matrix is built assuming the best alignments, and as we can see, the theoretical upper bound score on the top right triangle is S1 and the bottom trapezoid is S2. The narrowband score is optimal if it is larger than S2, but we can see about 30% of cases where the score is between S1 and S2 but are likely to be optimal. Where we could rerun these queries with full-band machines, we perform additional checks to filter more queries. If the narrowband score is between S1 and S2, we can prove that the potential optimal score outside the band must be obtained in the shaded region D if and only if such score exists. This is because we can use S1 as the upper bound score of the non-shaded region on the bottom trapezoid. So we just have to show the optimal score doesn't exist in D. The third check, E-score check, eliminates the possibility of the path entering the shaded region from the top. To do so, for each cell on the top boundary of D, we add maximal score increments to the E-score, assuming all matches for the rest of the query outside the band, and find the max. Rerun is needed if the narrowband score is smaller or equal to the max E-score. Finally, we check non-existence of the path entering from the left. We perform an extra extension using S1 as an optimistic initial score. Where the same affine gap scoring can be used, we use an optimistic scoring because it significantly lowers hardware complexity. Overall workflow is shown here. SeedEx check does not modify baseline accelerator design, but it can be added as a module that can be shared across many PUs. Now let me move on to our SeedEx Accelerator implementation. We implemented SeedEx Accelerator for Cloud FPGA. Our main Bandit-Smith-Waterman core has a generic design, but we built it from scratch. This is because we want to produce bit equivalent result as BWMM, so we included additional modules to fully support software optimization in BWMM for result equivalency. Edit machine is the key component to boost the passing rate of SeedEx algorithm. We introduced two important optimizations, delta encoding and half-width PE array. As can be seen in the figure, these two optimizations contribute to drastic reduction in area. The optimized large band edit machine is 83% smaller than the narrow band BSW core. Delta encoding uses residue arithmetic to reduce data path width. This is based on the insight that any score change is bounded by a fixed dynamic range. For example, in the edit distance scoring, scores of any neighboring cells of a cell scored x are between x minus 2 and x plus 1. Now let us map a pair of x and one of its neighbor xn to a modular circle of its circumference is larger than 6. Two scores and its transitions are always on the small arc of the circle. This allows us to figure out their magnitude relationship and the difference. And the data path just needs to communicate modulo delta values. Delta encoding can reduce the data path width from 8 bits to 3 bits. Based on the delta encoding theory, we built 3-bit DMAX unit and decoder. To decode a delta encoded value, we just need an original score and delta encoded score to align in an augmentation path. Finally, we integrate SeedEx with BWMM 1 and 2 and deployed it on AWS F1 instance. Several FPGA threads work together to hide data transfer and CPU process time, sharing several XDMA channels. An FPGA thread ready to use FPGA acquires lock and sends accelerator commands through OCL channels of PCIe. Let me move on to the evaluation methodology. We use Illumina 101 base pair reads of 50x coverage. We compare SeedEx with BWMM 1 and 2, Cusho 2 GPU, and Genax, which is presented in ISCA 2018. We used a seeding accelerator that we've developed called ERT. We validated the output of all 700 million reads exactly matches with BWMM's output. On the other hand, BSW core without SeedEx produces many differences. Also, with a band size of 41, the thresholding only passing rate is about 72% and the overall passing rate is about 98%. From this result, we determine the band size and edit machine ratio. Here we show our performance result. On the left we show ISO area kernel throughput. Due to reduced area, we achieve 6.0x throughput. SeedEx achieves nearly optimal throughput thanks to appropriate prefetching and buffering. The latency is 1.x lower than the full-blown code because register initialization and result accumulation time scales proportionally to the band size. On the right, we show end-to-end application performance. SeedEx and ERT achieve 3.75x speedup over BWMM and 2.28x speedup over BWMM2. Here we show the performance of our ASIC implementation. SeedEx achieves 20x better performance than SeedEx, which is Seed Extension Accelerator in Genax. SeedEx also achieves 16x smaller area and 10x less power for Seed Extension, which is translated into 1.6x better ISO area performance and 2.5x better energy efficiency. In conclusion, we propose SeedEx algorithm, its accelerator design, and its integration with software pipeline. SeedEx is 2.3x smaller than the full-band design and can also work as a lightweight optimality checker for unsafe narrowband design with only 5% area overhead. We achieve significant performance and energy efficiency improvements while meeting the validated quality standard. Thank you very much.